Welcome! In this video, we will discuss an example for the second case for the WKB or semi-classical approximation. This example is Gamow's theory of alpha decay, which is a very primitive way of modeling the alpha decay phenomenon. In case you're not familiar with alpha decay, it is a very simple process where we have some nucleus, let's call it X, right? It could be anything. And this will then decay and it will become some daughter nucleus, as is usually called, some Y, and also a helium nucleus. So basically just two protons, so one proton here, and two neutrons. So that is alpha decay. This is an alpha particle, right? That right there is an alpha particle. And for that reason, this is called the alpha decay. And it is a very, very, very common decay that you will probably encounter if you're working in any field that works anywhere near collisions or nuclear physics or medical physics or anything like that. You will encounter this sort of decay very, very often. So Gamow's theory of alpha decay is a very early attempt to explain this, and it uses the WKB approximation. Now, let's show what it is. So let's try to write down what this potential looks like. So if we have some particle, right, let's call this the 0 point, and now this is the distance from nucleus, right? Perhaps we should call it r instead of x. And if the particle is inside of the nucleus, then it will feel an attractive force because of the existence of the nuclear forces that keep the nucleus together. So up to some point, which we will call right here, I guess we can call it R1, which is the radius of our nucleus, it will feel the nuclear forces. So this is nuclear forces right there. So it has an attractive potential, these nuclear forces. After that, it will immediately jump because it is no longer being held together by these nuclear forces that decay very quickly. Okay, so that is one of the main things about the nuclear forces. They decay incredibly quickly as soon as you move outside. So that is why there's this big jump, and then it is repelled by the positive charges in the nucleus, because in the end, what do you have in the nucleus? You have a bunch of protons and neutrons as well, of course, but they are neutrally charged, so they don't really matter that much. So you have protons here and protons here, so they will repel each other. So for that reason, as soon as it is outside, it will feel this repulsive force. And the further away it gets, the smaller the potential will be, and thus, of course, smaller the force. So this is basically what models our situation. And now, what is the energy of the particle when it is in this bound state inside the nucleus? It will be some amount E, right? Of course, E is smaller than this value of the potential right there, right? Otherwise, we would have no nucleus. And this value, let me maybe do it like this. This value will extend, right? It will, and we can just extend this value. And at some point, the value will now be greater, right? At that point, the value will be greater than the potential. And in that case, that is what we call the turning point. This is the outer turning point. Okay, so those are our 2 points of interest, R1 and R2. Now notice that classically, the particle should not be allowed to leave the nucleus, right? That shouldn't be a thing. There should be no decay. However, experimentally, we know that there is a decay. And that is, of course, because of the phenomena of tunneling, right? This is a very good example of quantum tunneling. So that's just a little fun fact. So now let's begin, of course. What do we want to do here? We want to determine, well, a lot of things. We want to determine the lifetime of this X atom, right? How long will it take for the alpha decay process to occur, for example? So how could we determine the lifetime? Well, let's begin by looking at it like this. So if we have the nucleus And this is, of course, not the best way of looking at this, but this is, of course, a primitive way to describe this. We will have our alpha particle somewhere in here, and we can think of it as just basically moving around the nucleus in here, right? And having collisions with the potential every now and then. So, well, how often does this collision with the walls of the potential occur? Well, if we think of the radius, actually maybe do it like this, of our nucleus to be R1, as we already said, then the diameter is 2 times R1. And how long does it take our particle at most to go from one side to the other? It's going to be 2r1 divided by the velocity of our particle inside of this nucleus. So this will be the time for one collision, basically. Right? It's not the best approximation, but you know, it's an approximation. So what is going to be the frequency? Well, that's going to be 1 over this amount. So the velocity over 2r1, right? This is in units of seconds. This now is in units, basically the units of this will be 1 over seconds, which of course is hertz. So this will be the frequency of these collisions. Now, every single time that there is a collision with this wall, with the potential, there exists a chance that our particle will be transmitted, right? Because of quantum tunneling. So for that reason, if we want to find the probability of transmission per unit time, in this case second, then what we need to do is multiply the frequency that we found. So let's say probability, this is equal to the frequency that we found times the probability per unit times, I guess, so per second, the frequency of collisions times the probability of being transmitted, which we know is t. So what is f? F, we saw, is the velocity of the particle over 2r1, and we saw in the previous video that the transmission coefficient using the WKB approximation will be e to the minus 2 gamma. So this is the probability of collision per unit time. So the time it will take for this decay to occur is going to be 1 over the frequency, right? So that is what we call the period. Now, we usually use this tau here. So the lifetime will be 2r1 over the velocity of the particle times e to the 2 gamma. So this is how we describe the lifetime of this particle. Now, this is what we need to find. The velocity, however, as we will see, will not be particularly relevant, because what really changes is this exponent right here. The velocity will not be too big compared to this exponent, which can change, like I think it's like 25 orders of magnitude. So our goal will be to find this e to the 2 gamma. So let's begin. So we know, of course, that the transmission coefficient is e to the minus 2 gamma, approximately, of course. Now, what was gamma? Gamma was this integral, so it was 1 over h bar, integral of the momentum dx. So what is the momentum? The momentum, so this is, of course, the absolute value of the momentum, right? So this will be, let's see, it is square root of 2m. So let's put it like this. So we already get rid of that I, and now we plug it in. So we get 1 over 4 pi epsilon 0 2z e squared over r, and then minus e. Okay, and now we can make this notation quite a bit cleaner by using now the fact that we know that there exists this turning point. So at that turning point, the potential, so the potential at R2 will be the same as the energy. And that now plug in just R equal R2, we get 1 over 4 pi epsilon 0 2z e squared divided by R2. So basically the exact same thing. And notice that we have this thing there and this thing there. So we can now solve for that thing, right? So 1 over 4 pi epsilon 0 times 2ze squared. This is the same as e times r2. So let's plug that, there we go. Let's plug that into our formula for the momentum. So momentum is equal to the square root of 2m. And now instead of all of this, we get e r2 divided by r. And now we can easily factor out the square root of 2me times r2 over r minus 1. So there we go, that is the momentum. So let's plug that into gamma, because what we need to find at the end of the day is gamma. Now, gamma is 1 over h bar, the integral. Now, what are the limits of the integral for this problem? Now, our potential ranges from r1 to r2, at least that is where we have this turning point. So that is the part that we are interested in. That is the part where the energy is greater than the potential. Smaller, not greater. So we are going to integrate from r1 to r2. Of course, keep in mind, the limits of our integral don't matter, right? They come out as just this constant. Okay, now this is the integral of momentum, which is what we have right there. So square root of 2me, which we can pull outside of the integral. So right here, square root of 2me. And then inside we have r2 over r to the minus 1 inside a square root, so 1/2 dr. So now we need to solve that integral. So let me call this I1 and solve it here without having to worry about all of the constants. And then of course we will plug it back in. So r2 over r minus 1, 1/2 dr. Okay, so how do we solve this integral? Now it might look very nasty. It has a square root. My first guess would be to say, all right, what if I just use the substitution? U is equal to r2 over r minus 1. And let's see what happens. Perhaps it will be useful, perhaps it will not. But in an integral, there's a lot of cases where you can use substitution to solve for square roots, so perhaps this will be one of them. Now, in this case, so this is what is inside of the square root. Perhaps let's even do it like this. So u will be the entire square root, right? And I'm thinking of this because I know that when we derive this, we will get another one of these expressions which will simplify the problem for us. But of course, this is an art, right? It is much easier to solve integrals when you have already solved this sort of integrals. So if it's the first time that you are seeing it, don't worry. Okay, so what is the u? The u is going to be the derivative of this. Now, what is the derivative of this? It's going to be 1/2. Now, what is inside? So r2 r minus 1 to the minus 1/2, and now because of the chain rule we multiply by the derivative of what is inside, so r2 divided by r squared and with a minus sign, right? Because it was r to the minus 1, the minus comes outside and it becomes r to the minus 2. Okay, and of course dr. So what we need to find here is dr, because we need to plug dr into our integral. So let's do that. So to find it, let's multiply by minus 2 r squared over r2. So we get minus 2 r squared over r2. And then we need to multiply by this thing to the 1/2. So times r2 over r to the minus 1/2. Minus 1, of course. And this is du equal to dr. And there we go. Now we can write the integral, at least partially, in terms of u. So I1 will be integral from u1 to u2, right? We need to change the limits of integration. And then we have this same thing. So r2 divided by r minus 1 to the 1/2. And now the r, which is minus 2 r squared r2 r2 over r minus 1 to the 1/2 du. Okay, so let's do this step by step. So what is u1? Well, the limit 1 is r1. So if we plug in here, r equals r1, we get u1, which is square root of r2 over r1 minus 1. And if we plug in r equals r2, we get u2 is equal to 1 minus 1, so 0. Okay, so our integral goes from u1, which I'm too lazy to write, to 0. And then we have a bunch of constants, so we can write outside minus 2 over r2. Then we have r squared and r2 over r minus 1. And because we have 1/2 here, okay, let me do it like this. So 1/2 and 1/2, we get, of course, to the 1 power, and we don't worry about it anymore. Okay, so we are doing a lot of progress, and I just realized there's no parentheses there. Okay, now let's plug in r, because we still need to get rid of it. So r, we can find it from there. So let's do it perhaps to the side. So if u is this, then u squared is r2, right? This is from here, right? From there. U squared is r2 over r minus 1, and thus u squared plus 1 is equal to r2 over r, and for that reason, r is r2 divided by u squared plus 1. Okay, now let's plug that in. So this integral now minus 2 r2, that hasn't changed, u1 to 0. So r squared will be r2 squared divided by u squared plus 1 squared. And then we have r2. Now here I think it might be simpler perhaps if we just... Actually, no, I was thinking about maybe applying a common denominator here, but I think I'm going to leave it as is and see how easy this is. So r here is r2 divided by u squared plus 1 minus 1 and then du. Okay, so let's see, how can we simplify this? So these constants, they don't change. Then take a look at this. So we have r2 squared and r2. So let's allow them to simplify each other. So we get, instead of r2 down here, we get minus 2 r2. There we go. Then we have in here r2. So we have r2 divided by r2 divided by u squared plus 1, which is the same as r2 times u squared plus 1 divided by r2. So this thing right there is simply, so let me write this thing down first. So that is simply u squared plus 1. And then we have, let's see, u squared plus 1, yeah, minus 1 du. Okay, now we could go ahead and simplify these two things, but don't be so quick, because in this case, it's actually better not to do that just yet. So I1, let's rewrite this. So this is R2, U1 to 0. And now let's multiply through. So we get this and this, which cancel each other out partially. So we get 1 over u squared plus 1, and no longer squared. And then minus 1 divided by u squared plus 1 squared du. So here we have two integrals. Integral, let's call this I2 because I1 we already used. So just to be very clear, I2 is integral from u1 to 0 of 1 over u squared plus 1 du, and I3, which will be this thing, is integral from u1 to 0 of 1 over u squared plus 1 squared du. Okay, so let's solve each one of these. I2 is a pretty quick integral to solve. So I2, this is, now I hope this clicks something in your brain. This is a very, very common integral that you should learn if you don't know it already. This is the arctangent. So arctangent of u, evaluated between u1 and 0. But the arctangent of 0 is 0. So we get minus, let me write it as tangent to the minus 1 because I'm lazy, u1. And what is u1? Right, so this is minus tangent to the minus 1 of the square root of, and I already forgot. So u1, we wrote it down somewhere over here. There it is. It is square root of r2 over r1 minus 1. So square root of r2 over r1 minus 1. Okay. So that is the first result. I'm going to write it like this so that I can easily find it later when we need to plug it in. Now, what about I3? Now, I3 is a little bit more difficult, but it is not as terrible as it might look. So we have actually already solved equations like this in this channel. Of course, I'm going to show you again, but just so that perhaps you will remember it. The way to solve equations of the sort 1 plus x squared to the sum power is to, and we can even do it if there was some sort of constant here, right? Or even if this was not 1. So the way that we want to solve this is to think, all right, we have something squared plus 1. And we want to think which substitution could make that simple. And the answer is to remember that the tangent squared of some angle theta plus 1, what is this? So I'm going to just show it. So this is sine squared of theta over cosine squared of theta plus 1. We can take common denominators, so we get sine squared plus cosine squared. And that is, of course, 1. So we get 1 over cosine squared of theta, which is secant squared of theta. All right, so that is why using a substitution of the form u is equal to tangent of theta is very useful. And also because the derivative of tangent is precisely secant squared of theta, of course, the theta. So let's plug that in. So let's see, this is now I3 integral from theta 1 to theta 2, and then we have 1 over, we know that this thing here is simply secant squared, so we get secant squared of theta squared, and instead of the u we have secant squared of theta d theta. Now what are the angles theta 1 and theta 2? So theta 1 from here, we can see, or in general, before we go into the cases, so theta is the inverse tangent of u. So thus theta 1 is tangent to the minus 1 of u1, which we know is square root of r2 over r1 minus 1. And theta 2 is 0, because the inverse tangent of 0 is 0. Okay, so those are our two limits. So let's just write 0 instead of this. Okay, and of course here the secants will cancel out, and we get 1 over secant squared. And that, my friends, is simply cosine squared of theta. And this is a very easy integral, right? We simply write, instead of cosine squared, we write 1 plus cosine of 2 theta divided by 2. This, again, this is a very, very important trigonometric identity that you should recall. It comes from the fact that cosine squared plus sine squared is equal to 1, and also cosine squared minus sine squared is equal to cosine of 2 theta. So if you add these two together, you can find this formula, and if you subtract them, you can find a formula with a minus sign there, which is when you have sine squared. Okay, so that was just a quick reminder. Now let's integrate this, which is very easy. So doing that, we have integral, actually let's pull the 1/2 outside. So let's do it like this, so 1/2 there. So we have 1/2, and then integral of 1, that is very, very simple. That is theta, evaluated between theta 1 and 0. And then we have the integral of cosine of 2 theta, which is sine of 2 theta divided by 2, evaluated between theta 1 and 0. Okay, now what is this? So what is integral of 3? Now, this is 1/2 of, and this thing right there, what is theta 1? Well, theta 1, we know already. So basically, theta of 0 is 0, so we get minus theta 1. So I'm going to do this step by step. So minus theta 1, and then we have plus sine of 0, which is 0. And then we get minus 1/2 sine of 2 theta 1. Okay. Now, what is theta 1? So let's do it like this. So we get minus, and theta 1, we know, is the inverse tangent of r2 over r1 minus 1 square root. And then we have this sine. But what is the sine of 2 theta 1, or 2 theta in general? We know that the sine, I'm going to write it here as a reminder. So sine, this is another formula that you should know. Sine of 2 theta is 2 times sine of theta cosine of theta. So using that, we get 2 over 2 sine of theta 1 cosine of theta 1. Now the 2's, of course, cancel out. Okay. So now the question is, what is sine of theta 1 and cosine of theta 1? Now, to answer that question, let's remember that we know that theta 1, basically, or rather the tangent of theta 1 is equal to u1. So if we draw a triangle, so we make this triangle, right? These are, of course, 90 degrees, and we call this here theta 1. Then if the tangent of theta 1 is u1, it means that the opposite side divided by the adjacent side has to be equal to u1. So this side is u1, this side is 1. All right? And that means, of course, that this other side is 1 plus u1 squared and the square root. So what is then the sine of theta 1? The sine of theta 1 is going to be the opposite side divided by the hypotenuse. That's what it's called, right? In English, yeah, the hypotenuse. So that is u1 divided by the square root of 1 plus u1 squared. And what is the cosine of theta 1? Well, the cosine is the adjacent side divided by the hypotenuse. So that is 1 divided by the square root of 1 plus u1 squared. So let's now quickly calculate what is the product of sine of theta 1 times cosine of theta 1. So by doing this, we get u1 divided by the square root squared, so it goes away, of 1 plus u1 squared. Okay, now what is u1? Well, u1 is the square root of r2 over r1 minus 1, and down here we get 1 plus square root of r2 r1 minus 1. Now the minus 1 here cancel out, so that one's going to be simple. And now this is dividing, so we can write this as square root of r2, and let's actually take common denominator here, so we get r2 minus r1 divided by r1, all of this divided by r2 and multiplied by r1. So of course the r1s here will partially cancel each other out, and we get square root of r1, right? Because this r1 now becomes r1 to the 1/2. So we get square root of r1, which is this one, just to make it very clear. Then r2 minus r1 square root divided by r2. So that is the product of sine and cosine here. So let's plug it in right here. So this thing is square root of r1, r2 minus r1 divided by r2. Just double check. Yes. Okay, so this is the result of I3. So we can now just go ahead and plug everything into our integral I1 right here. Actually, I'm going to write it underneath. So I'm going to do it like this. Just zoom out, and that was a disaster. Let's see. There we go. So let's plug it in. So this first integral, so integral 1, we already saw, yields minus the tangent, inverse tangent, right, of square root of r2 over r1 minus 1. And then the second integral, or the one we named I3, that one yields, let's see, I already forgot. So what does the other one yield? Okay, 1/2. So that is, we can factor it out. We can factor 1/2. We can factor minus 1/2 outside. So let's do that. So we get plus 1/2. And then we have the inverse tangent of square root of r2 over r1 minus 1. And then plus the square root of r1, r2 minus r1, and divided by r2. Now, notice, of course, we can simplify a few things here. Now we have square root, sorry, the tangent here and the same tangent here. So we can just multiply through and get rid of this tangent. And that just means that there will be a 1/2 right there. And well, here we just multiply by 1/2. That doesn't really do much. Just 1/2 here. There we go. And finally, multiply through by minus 2r2. So by doing that, we get r2 times the tangent, inverse tangent, of the square root of r2 minus 1 over r1. And then we get minus, now the 2's cancel out, the r2's cancel out, square root of r1, r2 minus r1. And then finally, we can plug all of this back into gamma, because as you might recall, gamma was just the square root of 2me over h bar times I1. But we already know what I1 is. It is this very thing, right? R2, inverse tangent. Oh, wait, this isn't supposed to be that large. So just R2 divided by R1. There we go. So R2 divided by R1 minus 1 minus square root of R1, R2 minus R1. There we go. That is gamma. Now, if you're following a book like Griffith's, you might see a slightly different result. And I will show you how to compare them in a moment. So be patient. Now, the next thing we want to do, because this is not really an expression that we can do too much about, right? So what we now want to do is use an approximation, because we don't really know either R2 or R1 for now. What we can do is say, well, what we do know is that R1 is much smaller than R2. Why is that? Because R1 is the nuclear radius, right? It's the radius of the nucleus. So we know that the nucleus is very, very, very small compared to the distance where the potential is then going to be, smaller than the energy, right? This outer turning point right there. So we can use that approximation. However, using that approximation with our tangent here is going to be a little bit difficult. So for that reason, it would be much easier if we had it in terms of maybe sines or cosines. So that is where we now have to use a formula that relates the arctangent with the arccosine, and it is as follows. So now use the following. So the arctangent of sum b over a is equal to the arc cosine, and this is where we will now meet Griffith's result, a squared plus b squared. Now, in our case, we don't have it written this way, but we can easily do it. So let's take common denominator. So this will be r2 minus r1. And let's separate the square root just for clarity. So here we can clearly see that b is square root of r2 minus r1, and a is the square root of r1. So by doing that, we get that our tangent, I'm going to be lazy here, tangent is going to be the same as cosine to the minus 1, right? The arc cosine of a, which is square root of r1, divided by the square root of a squared, which is r1, plus the b squared, which is r2 minus r1. So as you can see, the r1s cancel out, and we are left with r2. So we have the square root of r1 over r2, or just compactly, the square root of r1 over r2. So in the limit, when r1 is much, much smaller than r2, what we have in here will be very, very close to 0. And what value of the inverse cosine gives us 0? Well, that is pi over 2. So cosine of minus 1, right? Sorry, the inverse cosine of theta, right? In this case, of course, theta is square root of r1 over r2. This will be very close to pi over 2, except for, just this very, very, very small quantity, just epsilon. It will be very close to pi over 2, but since this theta is not quite 0, then this epsilon is also not quite 0. It is very small, but not 0. So let us apply the cosine on both sides. So theta is cosine of pi over 2 minus epsilon. Now we know how to deal when there's a sum or a subtraction inside of a cosine. This is cosine of pi over 2, cosine of epsilon, since cosine is an even function, and then plus, since the minus sign will come out of the sign, right, sine of epsilon, right, the minus came outside and cancelled the existing minus, sine of pi over 2. Now this thing is 0, this thing is 1, so we get that this is the sine of epsilon. So basically, theta is sine of epsilon, but since epsilon is very small, we can approximate sine of epsilon as simply epsilon. So theta is basically epsilon. Now, why is that relevant? Because then we know that this thing right there is simply what we already have inside of the square roots. So that is simply r1 over r2. So that means that we can, instead of having cosine to the minus 1, right, the inverse cosine of theta, we can have pi over 2 minus this square root. So now let's go to our result and apply this approximation. So basically, now of course, maybe let's just write this as the inverse cosine. So this is cosine to the minus 1 square root of r1 over r2, right? This was the result that we had seen from Griffith's, and I just wanted to make it clear in case anybody was wondering. Now, instead of having this, we write this as pi over 2 minus, actually let me open the parentheses there, so minus square root of r1 over r2. Now, what happens to this other term in the limit when r1 is much, much smaller than r2? Well, in that case, this difference doesn't really make sense. r1 is so much smaller than r2 that we can simply neglect it, and we are left with r1 times r2. Okay, so then what do we have? So let's continue. So gamma in this limit where epsilon is basically when r1 is much, much smaller than r2, we get our constants, so 2me divided by h bar, and then we have R2 times pi over 2, and then we get minus, notice that we now multiply R2 times the square root of R2. So we get square root of R2 times R1, which we already have here. So we get 2 of those. So minus 2 square root of R1, R2. And there we go. This is basically our result. However, we can do better because R2 is not really something we know too much about, right? It is this kind of arbitrary amount. Where exactly is the energy the same as the potential? So we can now go back to our very old formula that we found somewhere up here. This one right there, right? We know that this is the value when the potential is the same as the energy. So for that reason, R2, we know, is 1 over 4 pi epsilon 0 times 2z e squared divided by e. So we can now very easily just plug this back into our equation. So there's no way I'm going to remember that, so I need to write it again. So where are we here? So we know that the energy is 1 over 4 pi epsilon 0 times, this is z times 2 e squared divided by R2, and thus R2 is 1 over 4 pi epsilon 0 times 2 z e squared divided by e. Okay, there we go. So let's now plug that in. So by doing that, we get square root of 2me divided by h bar, and then we get pi over 2 factor of. And now all of this. So 1 over 4 pi epsilon 0 times 2 ze squared divided by the energy. And then we have minus 2 times square root of R1. Now R1 is not an issue because that is simply the radius of the nucleus that is decaying, and that is something that we can easily know from experiments and we can find from other theories. And so that's something that we know easily. So it is okay if it's just a constant here, a variable for us. Okay, and the square root of R2, which will be square root of 1 over 4 pi epsilon 0 times 2z e squared divided by e. Now, most of these quantities are constants, right? So they don't depend on the element. So pi over 2, 1 over 4 pi epsilon 0, 2, they don't depend at all on the element. H bar as well. So we can put that all together into some constants and only leave out those things that do depend on the element, such as z, such as the particular energy, and also the radius, for example, so the radius of the nucleus. So by doing that, we can write this as some constant k1 times, let's see, z, so times z, and then we have square root of e divided by e, so we get divided by the square root of e. And then we have this other thing there, so there we have, we can write it still as a minus, and then some other constant, k2, and then the square root of r1, the square root of z, and the energies cancel out, so it's actually just like this. There we go. And what exactly are k1 and k2? Now k1 is, let's see, it is square root of 2m divided by h bar times 1 over 4 pi epsilon 0 times pi over 2. You could simplify a few things, but it's okay. Times 2z, no, not z, so 2e squared. There we go. So that is constant k1, and that has a value. Let me double check. It's e squared 4 pi epsilon 0. Yeah, we can of course simplify this 2 and this 2. This has a value of about 1.980 mega electron volts to the 1/2, right? Because the energy has to cancel out with the square root there. And the other constant, so K2, let's see, this is square root of 2m divided by h bar. Then we have this other 2 outside, and then square root of 1 over 4 pi epsilon 0 times 2 e squared. Right? I'm just double checking. In case for K2, we have e squared 4 pi epsilon 0. And then we have, yeah, these two. So basically this 2 and this 2, you can use them to go out of the square root. It becomes 4. And this here is 2 times 2, which is also 4. Okay. There we go. Okay, and just double checking again. I didn't remove this 2. There we go. And this is approximately 1.85 femtometers to the minus 1/2. So those are just constants, right? And what is important here is this result. Because if we now take basically any element and we put in its value of z, we put in its the particular energy that the alpha particle will have, right? And we also put in the radius, we can find gamma. And with gamma, we can find, as we saw at the very beginning of the problem, right here, we can find an estimate for the lifetime of the particle. So as you can see, the WKB approximation has allowed us to find this lifetime. Of course, the lifetime we can it's going to be ruled by this exponent. As I mentioned, we don't really know the velocity. We can know the radius, but not the velocity. But it will not be that much of a big source of error not knowing the velocity. The exponent is what really matters here. So basically what we did, just recapping here, all we had to do, although this problem may have looked very difficult, all we did was say, all right, the transmission coefficient is this, we need this gamma, and all we did was solve this one integral. That's all we did, because basically, there it is. This integral was the entirety of the problem. This integral, that was it. That's all we did. Find that integral. What we had I1, we had I2, we had I3, and then we needed to simplify a result. But if you think about it, it is a very simple way of explaining a very complex phenomenon. So yeah, I think that's pretty cool. So I hope that this video was useful to you. If it was, please, consider leaving a like on the video, commenting and subscribing, and maybe consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.